so today we are going to talk about course overview, pipettes, reagents, and lab safety. So obviously very riveting material. All right, so try to stay focused. Control your excitement. All right, lectures are at Mondays at 9 a.m. I know that's the hardest time slot. So kudos to y'all for coming today. Yay. And lab is at noon today to 2 p.m. So I recommend eating lunch beforehand so you're not hangry during lab. All right, so our course materials, the syllabus is located on the Canvas page. There's a little course syllabus quiz. It's super low key just to make sure that you've read it and you've gotten the highlights. It's due 8/27 by midnight. The course is organized into modules, and each module has learning objectives. You might be tempted just to not read these. I recommend reading these because these tell you exactly what I expect you to know, and they are a great way to make a study guide for the final exam. So hint, hint, nudge, nudge. We also have some pre-class assignments. That's usually just like, reading your lab so that you know what you're going to do when you come into lab, and also watching any demonstration videos. Some of them have me as Vanna White demonstrating things. So they're exactly what I expect you to be doing. Also, there's presentation materials. You should have access to the PowerPoints already. They're all up there except for one that Professor Muniz is teaching because I haven't poked and prodded him yet. And then we have lab materials on there, and then any additional resources, which are just like additional resources of things you don't have to do them, but they're helpful if you want like additional information. So there's like some extra videos and reading and stuff. And then we also have a textbook, Fundamental Laboratory Mathematics, as well. All right, so our learning goals. So at the completion of this course, the students will be able to, the students, achieve the following with 70% proficiency: identify common safety hazards, demonstrate proper technique to avoid accidents, so basically be safe. Identify and describe the appropriate use of PPE, describe the appropriate response to chemical or biological exposure, and operate basic laboratory equipment. So notice how I've underlined these little verbs in here. Those in learning objectives, those verbs kind of tell you to what degree you need to know something. So like discuss means you need to know more about it than just list. So there's different like levels of knowledge. And so these verbs will help you figure out how much do I actually need to know about this topic. So that should help guide your studying as well. So fun times. All right. Oh, there's more. Wait, my water bottle's broken. So you're going to apply theoretical knowledge, technical proficiency, and the selected laboratory skills. Apply the metric system of measurement, demonstrate lab practice standards, and recognize ethical issues embedded in the laboratory practitioner roles. So some of them sound kind of vague, but that's because some of them are very wishy-washy, like laboratory ethics. What does it mean? That's kind of embedded in all of our classes a little bit. All right, so some grading criteria. We have the safety modules that you did before orientation, and I've already gotten the printout from Professor Blameyer saying that everyone's done it. So yay, you'll all get points for that. There's a lab math quiz that you will do during open lab over the next few weeks. I believe that due date's September 17th. That sounds familiar. September 17th. So you'll have to coordinate with the lab staff for when to come in and do it. Then we have our lab assignments. So that's what like your microscopy worksheet that you turned in. That's considered a lab assignment. And then we also have first time this year. So y'all are my guinea pigs. The laboratory competency assessment, where we're basically just going to have faculty come in and actually watch you pipette and use a spectrophotometer so we can make sure that everyone's doing it correctly. Because when we're in the lab, there's so many of you and there's like really only one of me and maybe a few helpers. So it's hard for me to watch everyone to make sure you're doing it correctly. So this is a way for us to just check off that, yes, everyone knows what they're doing so you don't run into problems later on in the program. Then we have our phlebotomy competency assessment. This is done on a mannequin, not a real person. I'm not sure with the COVID out guidelines right now if we're going to be able to do it on real people, like to practice phlebotomy on real people, but we'll definitely do it on our mannequins. And I have named them because Armando, Manny, Brock, and Art. Then we have our effective domain assessment. So part of lectures, part of that. So that's things like coming in. Actually, there's another slide on this. So we'll skip that for a second. And then our final written exam and our final practical exam. So And then we have our grading scale. I think this is slightly nicer than the university scale. I think I gave you a 93 instead of a 94 for an A. So kind of built in a little bit of niceness in there. It's because I don't curve. And because of the program, you do need to make a 70% or higher in order to continue on in the program. All right. So the effective domain assessment, this includes things like attendance and punctuality, making sure it's coming into lab prepared and completing the lab, lab safety. So that thing includes things like wearing your PPE as appropriate, coming into lab dressed for lab, cleanup, professional behavior, and ethics. And then this is more detailed and like these are all based off of the program effective domains, effective objectives that are found in the handbook on page 7 and 8. And I'll be assessing these each week. And if I see someone's routinely having problems with them, I will pull you aside and be like, hey, we need to work on this so that way you can improve. All right. All right, course policy. So due to the hands-on nature of the lab, attendance is important, especially since this is only a half semester class. So if you miss a week, that's like missing like a huge chunk of the class. So no makeup laboratories will be routinely scheduled. There are some labs that are easier to make up than others, like today's lab. Super easy to like for the lab staff to set up, and other labs, it's just not as easy. So in the event of a valid absence, I'll try to coordinate with you to make up the work. And if you need extra help, please contact me. I'm very nice. I'm very friendly. I want you to succeed. All right, so now we're gonna talk about pipettes and micropipettes. All right, so pipettes, these are basically really fancy straws. So they're glass or plastic tubes at both ends that are used to transfer liquids from one container to another. And they're typically used for volumes between 1 and 100 milliliters. If it's under 1 ml, you're usually going to be using a micropipette because it's more accurate. Not to mention easier to use. All right, so there's different types of pipettes. This is where we get into the very riveting material. So there's volumetric pipettes. So these are designed to deliver one specific volume. They're extremely good at delivering that one specific volume, but that's the only thing they do. There's also graduated pipettes that can deliver a variety of volumes. There's more, and then there's serological. To be honest, no one really uses the more ones that much because they're a pain in the butt, which you will see why in the next couple of slides. But they do exist. All right, so the volumetric pipettes, these are used for very accurate measurements. You're going to use them a lot if you're doing like mass spectrometry or anything where you need to do a very exact amount. So these have a class A designation, which is basically a chemistry way of saying they're very accurate. And then to use it, you would aspirate up the liquid, fill to the little etched line, the bottom of the mist to the little etched line, and then allow the liquid to drain out into your new vessel while holding the tip against the vessel wall. And you do not blow it out. So you just let it drain by gravity, and whatever's left in there, that's what's left. Okay. So no blowing out. So a Moore pipette, this delivers a variable volume, and notice it's not graduated to the tip. So this is a 5 ml pipette, and you would have to stop the meniscus right here at this little line and basically keep the rest of the liquid in here to actually deliver 5 mLs. This is annoying. No one likes to do this, but they do exist. So you need to know that they exist and how to use them, but mostly you're going to be using serological pipettes. So you'd fill it to the 0 line, still once again rest it against the tip of the wall, and then do not allow it to drain completely because you want to stop it at that little line. Which once you start actually using pipettes, especially since we don't have the cool pipette guns, you will realize how annoying this is and why this is a bad design for a pipette, but they do exist. All right, so serological pipette, which are much nicer. These are also variable volumes. They're graduated to the tip. So basically this entire volume will get drained out, and they're more commonly used because they're not annoying. And these can, the fun thing about these is these can be considered to deliver pipettes or to contain pipettes, depending on the manufacturer. And it's important to know which kind you have because that will just decide whether you blow it out or not. So in terms of specifications, the maximum volume is at the calibrated line. So a 5 ml pipette, you might be able to get more liquid in it. If it's like a serological pipette, they usually have like a few milliliter lines above it, but 5 ml is where it's like calibrated to. So that's where it's considered like it's most accurate. It also will have the size divisions of the pipette. So this 1 in 10 means that it's at like 10th of an ml. And then the temperature the calibration was made at, so 20 degrees Celsius. And then it will also tell you if it's to deliver or to contain. So a to contain or TC pipette, that's when you're going to blow out that last drop because it contains that full volume. So you need to blow out that last little drop that the pipette is containing. And that usually indicated like a little double ring up here at the top of the pipette, in addition to usually saying like TD or TC. And then you also have to deliver pipettes, what will not have a ring at the top. And those, you just let it drain by gravity and you don't blow out that last little drop because it's designed to deliver the specified volume. All right, so it gets a little confusing. I get confused too, and I always have to look it up. But generally, you're going to blow out a serological pipette. Most of them are to contain. All right, so in microbiology, you're going to use these where you have these little pipette canisters, and these can be autoclaved, so you can put like glass pipettes in there, autoclave it, and then they're considered sterile. And when you get one out, you're going to lay the canister on its side and kind of like reach in as delicately as possible without touching anything else and grab the pipette you want, because you just assume that your hands are leaking bacteria everywhere. Just assume it's just raining bacteria everywhere that's under your hands. So you're going to try to minimize contaminating the pipettes and put the cover on immediately afterwards. No, there we go. All right, so there's different ways to get the liquid up into the pipette. So there's bulbs. There's my favorite, which is the gun. They're expensive, which is why everyone doesn't have one because they're about $400 each. So sorry, you get a cheap bulb. It builds character though. It builds character and patience. Never use your mouth. I feel like with this generation, this is just like, well, duh, of course I'm not gonna use my mouth. That's disgusting. But I've worked with professors who were old enough where that was a thing. So like pipetting blood, I'm like, gosh. Okay, and then there's many types of bulbs. We've got these that are these cool rolly kind. It's kind of like an old, I like them better than the bulbs because you can like roll it up and down so you have more control. Whereas with the bulbs, you got to fill it up and then you have to like magically put your finger over it and like slowly let it out till it gets to the meniscus gets to the line. It's just way more complicated. But we have bulbs, so good luck. I'd never understood these. We have a tutorial video on them, but I've never understood them. All right, so, ooh, I have a YouTube video.
I'm so fat. Brendan, you're not fat. It's the shirt.
I can't control that, guys.
Look at Nate. His true classic is tied around the chest and shoulders and arms.
Definitely tailored to me, right?
Serological pipettes are used to precisely deliver varying volumes of liquids. To accurately use a serological pipette, choose the correct pipette and bulb size. Select the pipette and bulb capacity that is closest to but larger than the volume needed. Some bulbs, such as a pipette filler, will allow for the pipette to be inserted, while others will simply cover the opening. Notice that the graduations on the serological pipette read from largest to smallest. This will need to be accounted for to accurately measure the amount needed. Hold the pipette between your thumb and middle finger in a vertical position over the container. Using the opposite hand, expel the air from the bulb and place it over the opening of the pipette. In this case, we need to transfer 5.5 milliliters of liquid. Immerse the pipette tip below the surface of the liquid. Release the bulb gently and evenly to draw liquid above the 4.5 milliliter mark. Be careful not to draw liquid into the bulb. Quickly remove the bulb and place your index finger over the opening. Lower the meniscus to the 4.5 milliliter mark by slowly releasing your finger. With your finger still covering the opening, withdraw the pipette from the container. While touching the inside of the receiving vessel, slowly release your index finger to empty the pipette. Serological pipettes are calibrated TD, or to deliver. To completely empty the pipette, use the bulb to blow out the last drop of liquid. Remind students to never pipette by mouth. With practice, your students will be pipetting experts in no time. As always, call us at Flynn if you have any questions.
All right, so that was so one thing with the bulbs, you want to fill it up more than you need because you're gonna have to like slowly drop it down. And I like how she just so ever so calmly put her finger over there. For me, it's like panic because I'm like, I'm not very good at the bulbs. So There will be definitely a learning curve today. All right. Well, I already watched all that. This is just it all written out for you. Boop. All right, micropipettes, my favorite. So these are usually designed to transfer volume between half a microliter, which is like this much, and 5,000 microliters. Most of the time, they're going to be under 1,000. Like 5,000 are like big mama jambas. Like you're just going to use a serological pipette at that point because those pipettes are expensive and the tips are expensive. So it's easier just to get a serological pipette or a volumetric. So they can be fixed volume or variable volume. Fixed volumes are more accurate at pipetting the volume that they are designated to pipette, but because they only do one volume, they're not particularly useful for a lot of other things. So a lot of times you're just going to see variable volume ones because then you can set it to whatever you want. And they can work by air displacement, which is the kind that we have in our lab. And they can also work by positive displacement, where there's actually like a little, it's like a piston that like, it looks like a little, like a metal wire with like a, not really a sponge, but like a cap on it. And it kind of like draws it up, kind of like a syringe, honestly. And those are really good for viscous things. So sometimes you get body fluids that are not particularly fluidy. And that's when positive displacement pipettes are utilized. I've had to pipette like an acidic fluid that came from someone with ovarian cancer, and it was like gelatinous. It was gross. Yeah. All right, so micropipettes, reading them can kind of be, reading the volume that they're set to can kind of be a little tricky when you first start because the scale changes based on the size of the pipette. So in general, like this is a P20, the 20 indicates that it's set, its maximum volume is 20 microliters. And you see the red number, that's the number below the decimal point. So this is the tenths place on a 20. All right, so this right here is actually reading 2 microliters, whereas this is reading 20.0. Whereas on a P1000, that red is at the top, and that actually indicates the thousandths place. So it's important to kind of know what the scale is on each one. And then they do have like little sub markings usually on ours. There's like little tick marks at the very bottom of the wheel, like right down where here would be. And that's where you could do like smaller increments, like 0.1, or for like the 1000, it'd be like, they're usually in increments of 2 microliters. So you can get a little bit more exactness for the volume you want. But there'll be some practice in today's lab on how to read these. And then there are multiple micropipette sizes, and they can transfer a range of volumes. So there's usually some overlap between the volumes that they cover. So we have a P10. We don't super use these in our labs. You might use them in molecular lab. The P20s, our lab, you're going to be starting off with the P100s and the P1000s, because where the P1000 goes to 100 to 1000, and then the P100 picks up right where the P1000 leaves off, so you can get all the way down to 10. So that usually covers what we need in our labs. But you can see how there's overlaps in volumes. And one thing is like these can both deliver 100 microliters, but you would choose the P100 because the P100 is way more accurate to deliver 100 microliters than the P1000 is, because you want to be the higher you are up in the range of that pipette, the more accurate and precise it is for that volume. So you always want to choose the pipette that volume is going to be in its upper range. You don't want to choose the P100 to do 10 if you have a P20. Like you always want to be at the upper range of the pipette because it's more precise and accurate. And you also want to avoid double pipetting. And that's basically where like, oh man, I have to transfer 2 mLs. I could get a volumetric pipette, which is annoying because of the bulb, or I could transfer 1000 twice with my P1000. And that's very tempting. Don't do it because it's not as accurate. But that is, sometimes people are like, oh, that seems way easier, but you're trading off in terms of accuracy and precision. So use the pipette that's appropriate for the task. All right, so how to micropipette. We're actually going to do this in lab today. So the plunger has 2 stops on it. So the first stop is like you just push it down and it's like where it gets a little bit of resistance. That's considered the first stop. And when you push down, and then if you push down a little more, that's the second stop. So first thing you're going to do is you're going to make sure you put a tip on the pipette. All right, so load your disposable tip. You can pre-wet it by pipetting up and down a couple of times. Some of our samples, because it's been centrifuged, you're not going to be able to pre-wet the tip. The pipette's more accurate if you pre-wet it, but it's not the end of the world if you can't based on your specimen type. So to fill it, you will push it down to the first stop, enter the liquid vertically. A lot of people try to go at an angle. It's not as accurate that way. So you want to enter vertically, enter the liquid, release the plunger slowly to aspirate. This is not a speed contest. The faster you do it, the more likely you are to get bubbles and be less accurate. Check for bubbles in any empty tips, and then dispense it against the sidewall of the receiving vessel and going down to the first stop. And then you go down to the second stop because that's basically blowing it out. That second stop, just a little extra puff of air to blow out that additional little droplet that's at the end. And if you aren't against the vessel wall, that little droplet's just going to end up on the outside of your pipette tip and not actually get dispensed. So that's why you want to be against your vessel wall. And then you'll release your plunger and eject your tip. And there's a fun little button on your plunger to eject the tip. You can ask, it's pretty fun. They shoot pretty far. It's a game sometimes. See your accuracy. We've had lab Olympics before. Competitions on how quickly you can fill a tip box. I can do it under 2 minutes.
Welcome to the pipetting tutorial, how to pipette correctly. I'm using a 2-button pipette. It has a control button with 2 stops and an ejector button. Pipetting starts when you attach the tip. Apply light pressure to insert the pipette into the tip. There is no need for force or moving from side to side. This would only strain your arm and damage the pipette.
Don't be the Hulk, basically. It will go on.
When aspirating liquid, 2 factors influence accurate liquid uptake: the aspiration angle and the immersion depth. The aspiration angle should be vertical. Otherwise, too much liquid is aspirated. The immersion depth, meaning the depth of the pipette tip inside the liquid, should be as large as necessary, but as small as possible. If the tip is immersed too deeply, additional liquid can be easily aspirated due to the capillary effect. Press the control button down to the first stop and immerse the tip into the liquid. Once the aspiration angle and immersion depth have been checked, slowly release the control button. Press the control button down to the first stop again and aspirate once more. Repeat this 2 to 3 times to saturate the air in the tip. When dispensing liquid, the angle of the pipette should be between 20 and 45 degrees, whilst the tip should stay in contact with the vessel wall. This guarantees optimal flow out of the liquid into the target vessel. Press the control button down to the first stop. Then perform the blowout by pressing further down to the second stop. This ensures that the tip is emptied completely. The last step during pipetting is ejection of the tip into a garbage bin by pressing the ejector button. Achieve accurate and reliable pipetting results with soft tip attachment, vertical aspiration, a low immersion depth, and a 20 to 45 degree dispensing angle directly in contact with the vessel wall. So,
There we go. I know, it's just so peaceful. I'm wondering why they chose green liquid against a green background though. That could have been better. Anyway, we'll talk to their production team. All right, so these are ways to break a micropipette, i.e. don't do them. Pipettes cost about $300 each, so don't break them. Number 1, never use a pipette without a tip, because then all the liquid would go up into the pipette. They don't like that. Never use it as a stir stick. It's not a stir stick. It's a very highly calibrated piece of equipment. Never set the micropipette on its side or turn it upside down when there's fluid in it, because what will the fluid try to do? It will try to go into the micropipette, which we learned does not like that. Never flame the tip or shaft. These are made of plastic. They do not like fire. If you need sterility, we have boxes of sterile tips. All right, those tips are just autoclaved, they're magically sterile. Use those. Never let the plunger snap back when you're aspirating or dispensing. So that's just basically being like, be like, ooh, ooh, slow and steady. All right. Never crank a variable micropipette beyond its range. So it's a P1000, stop at 1000. All right. They will go, you might be tempted to go higher because technically it will go a little higher. But if you go too high, it breaks like the innards of the pipette and screws it completely over, and it involves a lot of repair. So do not crank it higher than the specified volume. And don't drop it. We understand that you're humans, you might drop it. I have certainly dropped my fair share of pipettes. They're pretty hardy, but it does mess with the calibration. So if you do drop it, let us know so we can check to see if it needs calibration, okay? So that one's not the end of the world. All right, so micropipette calibration. So the manufacturers of micropipettes have like established precision and accuracy at various volumes, and they need to be calibrated periodically, usually every year or every 6 months, depending on the lab, to make sure they meet these accuracy and precision limits so that you are pipetting the volume that you think you're pipetting. And you can see here the P20 at 20 microliters, its accuracy is 0.16 microliters, whereas the P200 at 20 is 1.6. Like that's a big difference in accuracy. So this is why we always use the pipette at its upper range. We use the pipette where we can get the upper range. And its precision is also better on the P20 at 20. And same thing goes for the P100 at 100, its accuracy is 0.8 microliters, whereas on the P1000, 8 microliter difference. It is not very accurate at 100. So always choose a pipette that is at the upper range for the volume you want. All right. So micropipette calibration, this can be checked in a variety of ways. So you can check by setting a set volume of water, because water should weigh, like 1 ml should weigh 1 gram. It's magical like that. And you can measure it onto an analytical balance, and then calculate the difference from what you think you're pipetting versus what your scale said you pipetted. And you can calculate that mean difference, which would be the expected volume minus the mean volume, that absolute value. And then percent error is that expected volume minus the mean volume over the expected volume. That just kind of gives you like, okay, how accurate was I? And then precision is where you do that same volume measure multiple times, record those volumes, come up with the mean volume that you pipetted, and then calculate the standard deviation. I am never going to ask you to actually calculate the standard deviation. It is annoying. There's Excel for that. Okay, just a warning. I will ask you to use, I will give you the variance and expect you to know that variance and standard deviate, like make the square root of that is standard deviation, but I will never actually ask you to like do this whole little sum of whatever thing. And then you can also do coefficient of variation, and coefficient of variation is cool because it's if you're doing different like methods and different volumes and things like that, or different, like we have a large difference in numbers, it kind of corrects for that difference in size and kind of normalizes it all to like the same thing. So you can compare apples to apples instead of apples to oranges. And that's just standard deviation over the mean volume. All right, so you can also buy these fancy dye kits. They're expensive, whereas analytical balances, you usually already have one, so that's cheaper. But you can buy these cool dye kits where you have these fun little tubes full of liquid. You pipette out whatever volume you're testing, and then pipette out that same amount of volume of dye into it, mix it up, measure it spectrophotometrically, and they've given you these little standard dye tubes. And you can make a little standard curve and like plot it and calculate what volume you actually pipetted. They're kind of fun, but they're expensive. And you can only pipette, you can only check the calibration of as many volumes as you have tubes, for as many pipettes as you have tubes. So it can get very quickly very expensive. It can get very expensive very quickly. So a lot of labs will just do the analytical balance method. All right, chemicals, reagents, and reagent grades. This is where it's going to get even more interesting. All right. Chemistry definition of a reagent. That's a substance that is used to test for the presence of another substance by causing a chemical reaction. Or the broader scientific context, a substance or compound added to a system to cause a chemical reaction or added to a test if a reaction occurs. So basically, it's the chemical stuff we're using to test for our analyte of interest. So that's the reagent. Water is considered a reagent. They can be purchased at various grades of purity, and then not all those reagent grades are suitable for clinical laboratory use. All right, these are boring definitions. I'm sorry, you have to know them. All right, so analytical reagent, these are defined by the American Chemical Society, and they set these specifications for what's considered an analytical reagent grade. And they have to list like their maximum impurities. And this is suitable for most analytical laboratory purposes. So you'll often see these in the clinical lab. There's also the ultra pure grade, which undergoes additional purification steps. This is often used in things where you need it to be ultra pure, like chromatography, mass spec, immunoassays. These are often labeled as HPLC grade. It basically means it's super pure. What's funny is even though I know this is super pure, I would not drink HPLC grade water because it just seems it's coming out of a brown bottle. Don't ever drink anything out of a brown bottle. General rule for life. All right, then you have chemically pure grade. Impurity limitations are not stated and the preparation is not uniform. So this is just kind of like, we're going to do what we want. We know that what we're saying is in here is actually in here, but we have no idea what else is in there. So this is usually not suitable for the clinical lab unless additional purification steps are undergone in the lab or a reagent blank is used. You also have the USP and national formulary grades. These are usually used for like making drugs. And they don't meet the specifications for clinical laboratory assays for the most part. And then you have technical or commercial grade, and these are used in manufacturing, and this is really not pure at all. So this would never be used in a clinical laboratory. And you might be wondering, why do I need to know this? Well, one day, if you're a manager and you're in charge of buying reagents, you need to know what grade that you're using. All right, and then there's organic reagent grades. So there's still the ACS where it has certain impurities that have to meet a certain threshold. So you know its purity level. And then there's spectroscopic and chromatographic grade. So this is kind of like the ultra pure of the regular chemicals. Then you have chemically pure, which is similar to reagent grade, and then practical grade that has some impurities. And you choose your grade based on your desired applications. For most part, you're going to be in this reagent grade and chromatographic grade. All right, and then there's even grades of water. They have their own separate categories. Yeah. All right, so these are defined by the CLSI, and they're determined by specifications needed for use rather than their actual purification and preparation. So you have clinical laboratory reagent water. We use that. Special reagent water, instrument feed water, water supplied by the method manufacturer, which basically means the method manufacturer is going, this will work for what we need it to work for. Autoclave and wash water, and then commercially bottled purified water. And then there's different ways to monitor your water. So microbiological count, which is helpful if you're doing microbiology things, because you want to make sure it's not already contaminated with something before you plate or make agar. pH, resistivity, silicate, particle matter, organics. Each category has its own limits. These exist in the world. Now you know. If you ever need to know more about it, you will be taught by that person. All right, so there's different ways to purify water. There's distilled water, where you remove almost all the organic materials via distillation. Basically, you boil it, it evaporates, you collect that evaporation, because that should just be pure water, because all the other gunk stayed at the bottom. And then you have ultra filtered water, where you remove all the particulate matter, the microorganisms, any toxins. Then you have deionized water, where you've removed all the ions. You may still have organic matter in there, so it's not considered pure or sterile. And generally you deionize after you distilled or ultra filtered. So these are not necessarily done in like, you only do one of these. You can do like a series of them to get like the most beautiful water ever. And then you have reverse osmosis, where you actually use pressure to force the water through a semi-permeable membrane. Anything that is bigger than that pore sizes on that semi-permeable membrane stay outside of your filtered water. And you do these in sequence, so you can get like the best water for your application. All right. Oh my goodness. Okay, water purity categories. There's type 1, which is used for test methods requiring minimum interferences. This is like trace metal, iron, and enzyme analyses. This is very pure. Type 2 is what you're going to be using for most things. And then type 3 is like you're washing your glassware or preparing reagents. All right. Oh, yeah, we're ahead of schedule. Yes. Okay. We're going to start working on this. So that way we don't have as much to do in lab. All right. So lab safety, the goal of lab safety is to prevent accidents before they happen. I don't want you to get hurt. I don't want to get hurt. I don't want the lab to explode. All right. So over the past several years, there have been several high profile laboratory accidents that have led to significant injury or death. Luckily, not at the U. All right. So a Yale student asphyxiated in a lathe accident at a chemistry lab. She was working alone in the lab and her hair got caught in the lathe. A lathe is a thing that spins around. Like imagine like you're trying to carve like spindles on a post. That's what a lathe is. So it spins around and around and around. Her hair got caught in it and it strangled her. And since she was alone in the lab, no one was there to help her. And then there was felony charges filed against UC as well as the professor that was the principal investigator of this lab, where a research assistant was fatally burned when she was working with a chemical that she had not received proper training for. A syringe popped out of the back of the syringe popped out and the chemical was exposed to air, and that particular chemical is very reactive in air and it exploded and she died from burns several days afterwards. And with this lab had also received several citations about safety, and she didn't know where things were located, like the lab showers and things like that. So proper training was not done. It was a very tragic accident. And then Ohio State, chemicals weren't being stored properly and they reacted and things exploded. And luckily everyone got out on this one. No one actually got injured on this one, but obviously this is not great for your research if everything exploded. So this set them back several years and lots of money. All right, so even with training and careful attention to protocols, accidents can happen in the laboratory. We are human. So we want to practice, review, practice again, and then more review to help you respond quickly and appropriately should an incident occur. So that's like knowing where the fire extinguishers are, which for some reason are not actually in our lab. They're outside our lab. Don't know why. Where the eye washes are, where the safety showers are, what to do if there's a fire or something. So we want to know what we're supposed to do in the event of accidents. And one thing that we can definitely do is never be in the lab alone. All right, so as a student, you should never be in the lab alone. Always have a buddy. All right, so what are common failures in the lab? So these are things like that cause lab accidents, insufficient training. So you might be like, oh my goodness, I did all those MTS modules and now I'm getting safety again. That's so you have sufficient training. And we're always going to train you on how to use the equipment that we're using and anything that you need to know about anything dangerous that we're working with. So like creatinine reagent in chemistry, it's made with picric acid. And if you don't store it underwater, it explodes. So that's not cool. And then insufficient hazard evaluation and mitigation. This kind of has to do with you just aren't paying attention to where something could be dangerous and you're just thinking, oh, it's fine, nothing's ever happened before, so it's all good. So you want to kind of look around like a paranoid person and think what could go wrong, because it might go wrong. And you want to put something in place to prevent it from happening. And then lack of appropriate personal protective equipment. This is why we always want you to wear safety glasses, because those are impact resistant. And as appropriate, we will have you wear face shields, which are to prevent splashes from hitting you. And then failure to follow safety policies. So who's responsible for safety in the lab? Everyone but you two. So I'm in charge of making sure that you are trained. You are in charge of making sure that you did what you were trained to do. All right. So there's some support people on staff, environmental health and safety. Those are probably the most paranoid people I've ever met. But they do a fantastic job at keeping everyone safe. And there's also usually a compliance officer in every lab to make sure that everything is being done the way it should be. And then the department also has a responsibility to make sure things are staying safe. All right, so reporting. So we want to report incidents, near misses. So even though something bad didn't actually happen, we want to report that it almost did. So that way we can put some sort of control in place to prevent it from actually happening and having a bad event. So if you're just kind of like, that electrical cord looks a little sketchy, let someone know. We can get a new one. We can take that instrument out of use until we can fix it. So please let us know if anything you're just kind of like, I don't know if that seems safe. Please let us know. And then we want to prevent injury. All right, so a hazard is anything that can cause harm or adverse effect. A risk is the chance or probability that a person will be harmed or experience an adverse effect if exposed to a hazard. And the risk assessment is the process where you kind of go, what are the hazards? And then you evaluate the risk associated with that hazard, going, okay, what is the statistical likelihood that this is actually going to happen? And then, can I fix it? Can I make it so it's less likely to happen? So one example of a hazard is needle sticks. So back in the day, you would recap needles. That is not safe anymore. Now we have fun little needle shields that as soon as the needle comes out of someone's arms, you shield it. You don't have to come anywhere near that needle. And the risk of needle sticks has gone way down because of these controls and safety measures that we put in place. And then you want to perform your hazard identification and risk assessment prior to any new experimental procedures and new chemical usage or equipment usage, and kind of go, what could go wrong? How do I fix it? I am very good at this because I'm a very paranoid person. So I should work in environmental health and safety. All right, identify health and physical hazards to chemicals and equipment being used. So you want to read the labels, safety data sheets. So these will tell you the physical and health hazards. So physical hazards are like, it's flammable, it's explosive, it's a cryogen, like liquid nitrogen, it will like freeze your hand and burn. I did that one time. I accidentally let it pool in my hand and got a burn. It was not my best moment. I was a young little baby scientist. It was right after my freshman year of college. I was working at an NMR lab. They're like, oh, hey, feel it, roll off your hand. And I did it this way instead of this way. So it just pooled. It was not my finest moment. And then there's like process hazards. So anytime you're like adding heat and pressure to something, which happens in a lot of analytical chemistry labs, things can explode. When I worked in the lab where they were making MRI agents, and so they're doing a lot of like basic chemistry. And whenever the chemist started putting on PPE, I knew that things are about to go down because they were very like lax. And I was like, oh, they're putting on PPE. I want to step away. And then you also have health hazards. These are like irritants, corrosives, things that'll burn you, developmental toxins. So if you, for some people, if you do get pregnant, let us know. Or I guess you don't have to let us know, but we can tell you if there's anything in the lab that you're working with that is a developmental toxin, and to avoid that or put additional measures in place for you. And then there's routes of exposure, inhalations, a big one, skin contact, and we should not be injecting anything in the lab. So you're relatively safe from that one in our lab. But ingestion should also be relatively safe. So wash your hands. But inhalation and skin contact is our big one in our lab. And then you should receive training for new procedures and new equipment and report your concerns to your supervisor. All right, chemical label containers. This is riveting stuff. So there's two different ways to do this. There's these little numerical hazard rating systems. This is what you see on like the semi trucks driving down the road. This is just a fast way to say how bad is it for different categories. So a 4 is bad, a 0 is not bad. And then you have these little special symbols in the white box. So this one's basically saying don't add water. So the blue one represents health, the red one represents flammability, and the yellow one is reactivity. And then we have these HAZCOM standard pictograms. These are often on the actual like reagent label, and those give you kind of, these symbols mean like this one means a health hazard, flammable, exclamation mark basically means you need to look at the bottle a little bit more and figure out what it is. This is just a general warning sign. A gas cylinder, corrosion, exploding, flame over a circle means it's an oxidizer, environmental, so don't put it down the sink, otherwise you kill all the little fishies. And then the skull and crossbones means it's acute toxicity, which means it will be fatal or toxic. So that's what those are. We also have them bigger here for people who are blind like me. All right, so this is a reagent label. So this one has a little HAZCOM picture showing that it's toxic. It has the name of the chemical on it as well as its purity. And then we see down here, we have some additional warnings like may cause harm to the unborn child, harmful by inhalation. I'm not sure all that's in English. then usually have like your serial numbers and your like lot numbers and stuff. You'll always have your CAS number, which is its chemical identification number. And you can Google that and pick up and like look up SDS, like safety data sheet information from that. That's a universal SIG number for each chemical. Also has some like chemistry stuff about it, like what's its melting point, things like that. But hazard symbols, name are always on everything. Oh, there we go, hazard statement, your pictogram. And then here we have the nice big warning, and then it says all the things you should be warned about. This is acetonitrile. This is very commonly used in the lab. And I sometimes just treat it kind of like it's water. I should not do that. And then you have all your, this one has a numerical rating system on there in terms of its hazards. So instead of having that little diamond, it just has it written out with numbers saying the reactivity, the flammability, and the health. All right, so a lot of times you are not going to want to use a freakishly huge bottle of a reagent. They're unwieldy and they're annoying to use. So you're going to use a secondary container where you take some of it out and put it in a new container. So anytime you do that, you must make sure it is labeled appropriately. So these must comply with the following labeling requirements. You must identify what is inside of it. So you must say what's in it. And then you must include the appropriate hazard warning. So usually a lab will have like a little sticker sheet of these little symbols or the little diamond, and then you'd fill it in based on the original label so that everyone knows how dangerous it is and what it is. One of my pet peeves in life is people not labeling reagents. And since a lot of times these are like dilutions of something, please put what the dilution is. So that way you're not assuming it's 100% strength, and just label things so people know what's going on. All right, so hazard information resources. We have 2 minutes before. All right. You're gonna have your safety data sheets. Manufacturer are gonna contain manufacturer information, the chemical name, synonym, CAS number, ingredients, exposure limits, detailed hazard information, symptoms of overexposure and first aid. That's good to know. Chemical and physical properties, and then precautions for safe handling. So like with the picric acid, making sure it's stored underwater so it doesn't explode. It's also stored in the refrigerator. Things like that, and how it should be disposed of. In our lab, nothing goes down the sink. EHS only lets us put water down the sink, so we have those nice little green decant buckets for you to put it in, or we'll have a jug out for you to put it in. And then an SDS should be available for every chemical in the lab, either online or a physical copy. So we're going to talk about risk assessment. So we're going to identify circumstances of use, handling, and storage. So quantity matters. A little bit of something dangerous is a much bigger thing, is not as bad as a big amount of something dangerous, right? Got a little bit of alcohol, no big deal. Huge thing of alcohol, it spills, big deal. So quantity matters, concentration matters. 0.1 molar of hydrochloric acid is not as bad as 10 molar of hydrochloric acid. Then frequency of use, how often are you using it? Because that introduces opportunity statistically to mess up the more you use it. Experiment location. So, you know, if you can't be in a hood for something that has noxious fumes, be in a hood. Storage locations of flammables should go in flammable cabinets. Acids and bases should be separated, things like that. So try to minimize risk that way.
Nice to see you again.
And then we want to evaluate the hazards posed by chemical changes over the course of the experiment. So sometimes when you're doing a lot, especially analytical chemistry, things are going to be under pressure, they're going to be under heat, they're going to make heat. We do a fun test in urinalysis called the CliniTest. It's an exothermic reaction and turns lots of fun colors, but it also gets really hot. It like boils. So over the course of like 30 seconds. So this is one of those things where you have to think about safety, because if you're holding that tube in your hand and you start the reaction, you're going to get a burn. Gas production, and then other products of reactions and things like that. So just to kind of know what's going to happen and plan for that. And then consider additional hazards that may be scaled by posed by scaling up the reaction. So same thing, like 1 ml, not so dangerous, 100 ml, more dangerous. And then we need to identify appropriate controls as to how we can minimize risk. So they fall under 3 categories. Administrative controls. So these are things like signage, like that beautiful sign that says no food or drink allowed in the lab. That is an administrative control. Training, procedures, prior approval. So things that you have to like getting signed off on, yes, you're capable of doing this test or using this reagent or whatever. And then you have engineering controls. Those are like physical things, like this room has HEPA filters in it. So the air gets recirculated about every 10 minutes in this room, which is cool. Gas cabinets, storage cabinets. We have our nice big, huge flammable storage cabinet in the prep room where all of our flammable reagents are stored. Shielding and isolation. So we do have fume hoods to use, and then personal protective equipment like our safety goggles, which look super cool. Face protection, gloves, clothing. So that's wearing our nice long pants, wearing our water impermeable shoes, and then respiratory protection, because there's sometimes, if you're especially if you're working in microbiology, you might need to wear an N95 respirator if you're like working with TB samples. So making sure you're wearing the right thing for the procedure you're doing. All right, so our administrative controls, there's required laboratory safety training, like when you're a new researcher coming on, chemical hygiene training, other things required by EHS, like laser safety. Apparently you're not supposed to shoot each other in the eye with those. Who knew? Radiation safety, waste generator. And radiation is relevant to our field because sometimes we use radio assays, radio immunoassays, or in the blood bank, you'll also irradiate blood samples or blood products before giving them to certain patient populations. Lab specific training. So what you're actually doing in each lab, the SOPs you're supposed to follow. SOP stands for standard operating procedure. That is basically what you are supposed to do each time you do a procedure. That is the standard operation for that assay. Specific hazards to the equipment, and well, the equipment that you use. And that includes like laboratory signage. We have signs outside the door saying contact so-and-so in case of emergency. Then you can request signs from EHS. They love signs. Yeah. Too far. Okay, so our engineering controls, those include things like our fume hoods. You always want to work 6 inches into the hood because of the way the air circulation blows. It works best if you're at least 6 inches in. You want to elevate large objects so they don't block the ventilation holes that are along the walls. Don't use the hood for excessive storage. Some people just use it like it's a storage cabinet. It's just chock full of stuff. And you're like, how on earth do you have anywhere to move in there and do anything? So you very much just kind of want the stuff that you need immediately in there. Follow the instructions for the sash position. A lot of times they will beep at you and yell at you a lot if the sash is not in the right position. And then avoid rapid movements because fume hoods work by controlling the way the air circulates. So if you move quickly, that messes up the airflow. Whereas if you move slowly, you don't mess up the airflow and the air stays where it's supposed to. And then there's alarms if it's not working, and they're supposed to be inspected regularly, at least once a year, and they get signed off on to make sure they're functioning. All right, so there's other types of laboratory ventilation. So this guy right here, we have a little ventilation hood directly above the instrument. This is a cool hood as well. You can actually like put your hands in the holes and do your experiment. This one's a kind of like biosafety cabinet. So this is for the bad bugs that you don't want any contact with. Then we have our storage cabinets. So all flammables should be kept in flammable storage. There's also flammable freezers because you have some reagents that explode if they get too hot. So they have flammable freezers. I worked with one that if it wasn't kept like below -50, it would like explode. So you always had to like have liquid nitrogen when you took it out and like put it in the liquid nitrogen. It wasn't stressful at all, right? Then you have corrosive storage cabinets. You want to make sure chemicals of different classes are segregated. So acids are separated from bases. Oxidizers are kept separate. Water reactive reagents are kept away from water. And pyrophorics are also treated appropriately. All right, so compressed gases. So compressed gas cylinders have mechanical and possibly chemical hazards. So this is a compressed gas. And as we've seen in JAWS, if you shoot it or if something happens to it, it can explode. So it's great if you have a giant shark. It's not great if you're in the lab. So you want to make sure that they're stored properly. They're supposed to be like chained to the wall. And we have special transport carts for them. So that way that minimizes the risk of them falling and popping, exploding. You always want to make sure that you're using the correct regulator and tubing for the gas cylinder that you're using. And you want to make sure if it's a toxic gas, if you're in a well-ventilated area. And incompatible gases must be segregated. So I worked in an NMR lab where NMRs can quench where all of a sudden all of the liquid nitrogen or helium gas can like explode out of them. And they're like, if that happens, run. That was the directions, like just go, because all the oxygen in the room will go away. So fun times. All right, so personal protective equipment. I just want to say they do not quench very often. This is like a catastrophic thing. Okay, this is not standard. So personal protective equipment, proper laboratory attire. So we have our fancy lab coats that are knee length because we're for sitting. We don't want something to fall in our lap because that would be gross. We want it fully buttoned, so if anything splashes, it doesn't get on our clothes. Face shield if we're doing anything that where there might be splashing. So a lot of times if we're having you open patient samples, you'll wear a face shield so that if it splashes when you open it, it doesn't get on your face. Safety glasses in case of impacts. Long pants without rips or holes. If you do have rips or holes, we have very fashionable tape for you. Full coverage shoes like sneakers, we do prefer if they are not the meshy kind. So they must cover the top of your foot. So like little ballet flats or Mary Janes or those little short loafers don't count. They must cover your toes and the back of your heel. So the reason why we care about the back of your heel is if you're standing over here and something happens and you can just scrape your heel against the back of something, and that's happened where people have caught themselves and injured themselves on like the back of the metal grate of a refrigerator. So that's why we want the back of your heel covered too. Safety. Long hair is tied back, so it's not in your way. Doesn't get trapped in anything. It doesn't fall into your experiment. Gloves. So usually nitrile or latex is going to be sufficient for our uses. You might need chemical resistant depending on the task. We will let you know if that is needed and we will provide those gloves. So other things that may be required, face masks, yay COVID, and respirators, you'll be fit tested for those as needed. All right, so we had our little hand washing thing in lab, just a reminder, got to get all the surfaces between the fingers, the tops of the fingers, around the thumb, get the wrist, all that jazz. Do it for at least 20 seconds, singing happy birthday a couple times is sufficient, or pick your favorite song. All right, so then disposal of laboratory waste. You want to discard it into the appropriate containers. So glass goes in the non-biohazard trash. If it's biohazardous and it's broken, we want it in the sharps container. If it is a sharp, it obviously goes in the sharps. And liquids will go in the decant buckets or in special jars, or as we learned in orientation, like the big urine cups, chuck it all in at once, okay? So my general rule with trash is if the item you are trying to throw away is floppy, it can go in the floppy trash. I consider this the floppy trash because it comes, we just take the entire bag out, so then it's a floppy bag. If it is sharp and pokey, it goes in the hard pokey trash. That's my general rule of thumb. If you are uncertain, please verify with an instructor and we will either debate it amongst ourselves or we will go, oh yeah, it goes in there. So. All right, biosafety in the laboratory. So you need to have systems in place to prevent the transition of disease-causing infectious agents. These include HIV, hepatitis, staph, strep, and Mike, you're going to be working with live cultures of Salmonella and Shigella. You do not want to get Shigella. Trust me. Tuberculosis and herpes. So all of these things that are capable of being in our lab because we are a BSL level 2 lab. And you're like, oh, but I'm not working with that today. But how well did you clean up last time? Or who, you don't know who was in here last time either. So just always assume everything's disgusting in here. All right, so standard precautions. This is an infection control process designed to reduce transmission of infectious agents between patients, hospital personnel, laboratory personnel, etc. And it's a system of barrier precautions whenever contact is anticipated, with the basic understanding that you treat every sample as though it is potentially infectious. Because a lot of times you do not know if someone has HIV, you do not know if they have hepatitis. So you just assume everyone does and treat it appropriately in order to protect yourself. So the body fluid, so we have contact with any of these like body fluids, blood, sweat is not considered infectious. Otherwise the gym would be a very dangerous place. Secretions and excretions, tissue, non-intact skin as well as mucous membrane. So you just want to touch your face and your eyes or anything. If you have any cuts on your hands, you want to make sure that you cover them with a Band-Aid. That way, if anything does spill or your gloves puncture, it's not going into an open wound. All right, so if you have a biohazard or infectious spill, you're going to wear your PPE, which you should have already been wearing if you were working with something. You will contain the spill, making our little paper towel barricade that Chris demonstrated last week. Then you will cover it with more paper towels, and then you will saturate it with 10% bleach. Let it sit for 10 minutes so the bleach can do its stuff and kill everything. And then you'll just sweep it all into a dustpan and dispose of it in the biohazard. And then I like to do an additional little bleach coverage just to be safe. Clean it up. We do have our biohazard spill kits in case the spill is larger. All right, fire safety. The fire extinguishers that are outside our lab are what we should be using in here. There are different grades of fire extinguishers based on what you're most likely to be trying to extinguish. And then if there is a fire, you will try to rescue anyone if possible. You will sound the alarm, which is located over there by Kara. If you could van a white for me, Kara. No, that's not Kara. I don't know who that is. Okay. You'll try to contain it if possible. So we have fire doors that will help contain it. And then if possible, you will extinguish it. And if you were trying to extinguish it, to use the fire extinguisher, you'd pull the little pin, aim it at the base of the fire, squeeze the handle, and do sweeping motions. Fun story, we have a fire extinguisher in my kitchen because we know safety, and it was down on the ground, and my 1.5-year-old son found it, and he pulled the pin out, and we do not know where it went. Luckily, he did not do anything more. It has now moved to a higher location. All right, so electrical safety. Extension cords and power strips, those should only be used if necessary, and they really shouldn't be there all the time because they're more likely to pose a fire hazard. If they are there, you should secure them to prevent tripping. So like tape them to the ground with like fun colored tape so people see them. Don't daisy chains. A daisy chains where you're like linking a power strip with an electrical cord, you know, like where you just do lots of them at one time, because that just is not cool. And then they're each listed for a set electrical load. Power strips must have a circuit breaker on them. Don't use anything with damaged cords or plugs. I swear some of these are like super sketchy. Look at this. It's missing the grounding thing. Probably because the wall they were trying to plug it into didn't have a grounding outlet. And they're like, I'll just rip it off. It'll be fine. It might not be fine. We have this guy who looks like he's smoldering, has melted at some point. Highly questionable. And these people have an adapter, like a converter, and like an extension thing at the same time. It's barely hanging in the wall. It's just super sketchy. And then, so when we do electrophoresis, some of the older electrophoresis machines will often use like an alligator clip to like attach to the power source. So you just want to avoid that because if you touch that area, it can shock you. So now we have ones that are more like actual plugs because safety. This is an example of we've identified the hazard. We have made a correction for said hazard by not having alligator clips. All right, here we go. So general guidelines, don't touch electric things. Use guarding around exposed circuits and sources of live electricity. Remove jewelry when working on electrical equipment. I assume they don't mean just your standard like plug-in thing, but you know, if you're like, oh yeah, I'm gonna be doing electrical work, I'd take off your jewelry. Ensure hands are dry. Wear non-conductive gloves and shoes with insulated soles. Minimize the use of electric equipment in cold rooms and other areas where condensation is likely. If something is spilled onto the equipment, shut off the power at the main switch and unplug the equipment, and then deal with the spill. And make sure you let it all dry out before you turn it back on. Disconnect the power source before servicing or repairing electrical equipment. And if it's high voltage, get a trained electrician to come in. All right, don't try to do it yourself. If it's safe to do so, work with only one hand, keeping the other hand at your side or in your pocket, away from all conductive material. So you're kind of like James Dean doing stuff over here. If an individual comes in contact with a live electrical conductor, don't touch the equipment, cord, or person, because the person is now part of the circuit. So do not touch them if they are currently being like electrical. electrified. Disconnect the power source from the main switch, pull out the plug using a leather belt or perhaps wood. I'd be amazed if you had a leather belt, much less wood, but try your best. Nothing metal, and then call 911. All right, so equipment safety. Please do not remove or alter the guards in place to protect you. Don't mess with them. Wear safety glasses that have side shields. Remove jewelry that can be caught in the machine. Tie back hair and roll up sleeves. Because remember our poor Yale student whose hair got caught in the equipment and she strangled. Do not work on equipment until you have been trained, and never work alone. All right, so our chemical safety, wear the appropriate PPE, utilize the appropriate engineering controls based on the chemicals you're using. So that means using chemical resistant gloves if needed, using a fume hood, splash goggles and face shields, storing the chemicals safely, and then disposing of the chemicals safely. And in our lab, we're either going to have a jug out for you if it's something that we don't want to just be breathing it in, or we will have a nice decant bucket next to the sinks for you. And make sure you don't mix incompatible chemical waste in the same jug. All right, spills should be cleaned up in a timely fashion. If it's too big of a spill, call 911 and EHS. 911 if it's an emergency, EHS if it's like non-emergent. And then close the fume hood if you're in a fume hood, which hopefully you are. Small spills can be cleaned up by the lab staff unless they're toxic or flammable. And notify safety or emergency response personnel if there's any unusual safety hazards. All right, so in an emergency, we have our eye washes. There's at least one in each bay. I don't want to move too far away from my microphone here. So you got one over there. They're yellow. They have little yellow or orange caps on them. They should flush your eye for 15 minutes. 15 minutes is a really long time. This is why we wear safety goggles. Nobody has time to be flushing their eyes for 15 minutes. It's not a pleasant experience. I was cutting up a jalapeno and I touched my eye. It's not good times, guys. So don't try to avoid that. We check the eye washes weekly so they don't get all gunky. And then the facility checks them annually. Make sure you're not blocking them so that they're easily accessible to whoever needs them, because keep in mind they're going to have something in their eye. So they're not going to be able to see to navigate around obstacles. Safety showers, we have them outside the labs. You're going to pull the thing and make a huge mess. You're going to flush for 15 minutes. Remove clothing under the shower. We will come and shield you. And then facility management checks annually. Also make sure these are not blocked. All right, seek medical attention if needed. So if you have eye contact with a chemical exposure, you do this after you've done your 15 minutes of flushing, because we want to immediately kind of triage it before we go and seek additional medical help. If you have a significant chemical exposure, or if you have symptoms of a chemical exposure, such as inhalation of something that's causing coughing, burning, or severe irritation, electric shock, or laser injury. All right, so we're going to do some little what would you do, and these have some there's not like a hard set correct answer. So this is what would you do, or what should you do? So you are the first one to arrive for lab. No other faculty, staff, or students are present in the lab. You smell an unusual, unfamiliar chemical odor that is very strong and makes you cough. What should you do? I like to leave. That's my first plan. 1, you're not supposed to be in the lab alone. 2, we know it's not safe in there right now. So let's leave. And then what should we do after that? Yeah, we should call someone. Yeah, call EHS, call 911, notify the lab staff. We have numbers for the lab staff on the doors outside. So let someone know and don't go in. All right. Don't be a hero. All right. Second situation. You were the first one to arrive for lab. You notice about 2 inches of water covering the entire floor of the laboratory. What should you do? Yes, leaving is a great option. And notify someone. Leave and notify. And the things in water, I'd be like, okay, where's the electrical stuff? Can we turn off where's the main power switch? I don't know. So notify someone, they'll know where the main power is, but do not go in. All right, you're the first person to arrive for lab. You know that you will need to use the small tabletop centrifuge for the day's lab procedures. You plug the centrifuge in the outlet and you immediately notice sparks and some smoke around the outlet. what should you do? Not a clear cut, right? You're already in here now. Already plugged in. Things are happening. There's no right answer. I mean, there's better answers. I don't even know what the right answer is. Yeah, but it's smoking and sparking. I wouldn't want to touch it. I feel like it's not a fire though. It's electrical malfunction. So I'd be like, okay, where's like the circuit breaker? Which I really should know where that is. Somewhere. Maybe over there. Actually. So you want to like cut the power off to it somehow. I think these might actually have little buttons on them where you can turn off the power to the blocks. All right. Once again, you're the first one to arrive for lab. You are just very go-getter here. After entering the lab, you notice another student lying on the floor. I guess you're not the first one to arrive for lab. And the student appears unconscious. What should you do? Yes. Yeah, so I think the first thing is you make sure it's safe for you to like go in and it's safe for you to like touch them and assess them. So safety, your safety. And then we need to call 911 and then we can go in. Once we've determined that it's okay, it's probably just safe. We can like assess the student and try to help them, okay? But number one, before you touch them or do anything like that, make sure it's safe to do so. Because if they were electrocuted, you don't know if they're still part of the circuit. Yes, exactly. You don't know when the third person is going to be there. So we don't want to make the problem worse. So always make sure it's safe to help someone before you do it. It's kind of like on the plane, put your own oxygen mask on first, then help the person beside you. Okay, you're working in pairs. You're not alone. Yay. To complete a laboratory test procedure, your partner accidentally breaks the tube, which cuts through their glove. You can see that there is evidence of bleeding and pooling of blood in the palm of their hand. What should you do? This one's actually much more likely to happen. Yes, I like that. Get them to the hand washing station. So you're going to flush that area. You want to take the glove off, try to rinse out, because if we don't know what's in that tube that they were cut with, it could have been patient sample. So we want to flush that so that their risk of them getting a bloodborne pathogen is low or a chemical exposure is lower. And then obviously notify an instructor so that we can go through the appropriate steps to get them to medical treatment and things like that. But to the station to rinse it out. Make sure you're wearing your gloves when you're helping them because you don't want their blood on you either. All right, so that's where we're at. I'm going to stop this. Stop.